Hi, welcome back. Let's remind ourselves, what was the problem that we were attacking previously? We had some scatter of data, and we hypothesized that that scatter of data could be modeled linearly, meaning our hypothesis is that y is a linear function of x. In other words, y equals mx plus b. But we had a little bit of a hard time finding values for m and b. So now the question is, how do we choose those values? Well, now we'll talk about a cost function. And our cost function allows us to choose the right values of m and b so that our predictions are as close to our real output as possible. And a real output can also be referred to as a ground truth. What does this mean? Well, we have some x and we have some y pairing that are written down. So we can say for 5.5 hours of sleep, this student got an 80 on his exam. Now we want to be able to model that relationship linearly and have our model take that 5.5 as an input, put it through mx plus b, which is our hypothesis, with some values of m and b, and output something as close to an 80 as possible. Okay, this seems realistic. How do we do this with a cost function? And what even is a cost function? Well, the cost function allows us to evaluate the error of our model. And the error is measured by the squared distance between y hat, which is our prediction, and our ground truth. And we'll get into the equation of the cost function in just a minute. But the overall goal is we're measuring the distance between our prediction and the ground truth and trying to minimize it, meaning we want our model to be as accurate or as close to the ground truth as possible. So what is this cost function? How is it formulated mathematically? So in this specific problem, we'll be using a cost function called mean squared error. Okay, let's break this down. What do each of these individual letters mean? Well, 1 over n. N denotes the number of samples. So we're taking the mean here, the average sum of the differences squared between our prediction and our ground truth. Okay, 1 over n, so 1 over the number of samples, and then the sum of the squared difference between our ground truth and our prediction. Hopefully this is clear. And if it isn't, take a minute to write down the significance of each of the variables as we've defined them previously and try to understand how they interact. If you're having any trouble understanding the equation for mean squared error, make sure to send a message in the curriculum help channel in Discord. Now, mean squared error be reformulated to make things a little bit more simple. Mean squared error is really a function of m and b, because remember in our previous equation, we had this y hat variable. Y hat is really our equation, mx plus b, right? So mean squared error can really be formulated as a function of m and b, where mean squared error equals 1 over the number of samples times the sum of mx plus b minus our ground truth squared. Okay, not too difficult. Now, let's visualize what all this math means. Well, we start with some line that we think is pretty good, and we measure the distances between that line and our points, denoted by these red lines. So we're measuring the distance. Okay. We see that the distance between some points is larger than other points. It means that we might need to slightly rotate the green line, change the m and b values, kind of like knobs and dials, slightly changing the slope, slightly increasing or decreasing the y-intercept so we can minimize these distances. Remember, that's the goal. minimize the distance between the line and the points. Okay, let's simplify things for a minute. Let's say that our b value was always 0, and our equation for our line went through the origin, and our equation was y equals mx, meaning that m is the only variable affecting the cost. M is the only variable affecting the accuracy of our linear model. Let's say we plotted the cost function relative to our value of m. There's some value of m that optimizes the cost function so that it is at its lowest, meaning that there's some value of m that ensures that the cost function is small, or there's some value of m that ensures that the value of cost is at its lowest. Okay, and we see that there are values that ensure that the cost is really high, like on the edges here. The cost is really high when the m value is on the extremes. And then as we get to some minima, there's some m value that's perfect, that ensures the lowest cost. In 3 dimensions, when we choose to use m and b in our equation, we can see that it produces a 3-dimensional graph. We're adjusting values of m and b simultaneously, and this affects the cost function. And you see that there's some low point, that blue little low point at the bottom, where there's some combination of m and b that ensures the lowest possible cost. So now the question is, how do we find that lowest point? Well, we use a process called gradient descent, and we'll discuss this in the next video. I'll see you there.